Hi, my name is Wronski. I'm going to present our work, Filtering After Shading with Stochastic Texture Filtering. It was published at ACM SIGGRAPH Symposium on Interactive 3D Graphics and Games, known as I3D 2024. This work was a collaboration between Pharr, myself, Marco Salvi, and Marco's Fajardo. Let's start by reviewing the traditional approach to textures and texture filtering and how we teach it. I don't think I need to convince anyone working in computer graphics that textures are one of the most important building blocks for high-quality visuals. They are ubiquitous because they can represent rich surface detail and any kind of information, not limited to just color, but also, for instance, physical material properties. They can be compressed very efficiently and are a very compact representation, independent of the geometric density. Artists can easily understand and edit textures using traditional image editing tools. And textures are not just limited to surfaces, but can store volumetric 3D information or even 4D animations. Okay, but what is a texture? We often think of textures as images, but mathematically, a texture is a grid of discrete values defined only at the texel centers. To quote Alvy Ray Smith, pixel is not a little square, and similarly, texel is not a little square. Instead, it's an infinitely small point, mathematically known as Dirac delta. Those infinitely small points by themselves are not very useful for rendering. When we use a texture during rendering, we never hit an infinitely small point, and we need to evaluate the texture value at an arbitrary position in between. To do that, we use a process called filtering, interpolation, or sometimes reconstruction. Texture filtering takes a weighted average of multiple texture samples. The weights of those samples depend on the relative position of the evaluated point and contributing texel positions. While many filters, such as higher-order interpolating filters, have negative values and weights, all useful texture filter weights sum to 1 to preserve constant values in the surrounding neighborhood. In this traditional approach and framework of texture filtering, we also need to take special care for minification, namely when multiple texels cover a single pixel area, for example, because the shaded object is very far away. There can be thousands or even millions of contributing texels, and we cannot select just one or a few of them, because doing so would result in aliasing. So, in this traditional framework, we can use two solutions. We can use full filtering, for example, elliptically weighted averaging or anisotropic filtering, where we evaluate all of those samples and we use weighted averaging. This has the downside of possibly being very slow, taking hundreds, thousands, millions of texture samples. On the other hand, this solution is of higher quality than the alternative used mainly by real-time renderers, pre-filtering. Pre-filtering is typically implemented as creating an image pyramid of lower and lower texture resolutions called mipmaps with high-frequency content removed. During the runtime, we fetch the texel values only from mipmap levels of comparable resolution and texel density to the screen resolution. This is a much faster solution, as for trilinear filtering and trilinear interpolation you can take only 8 samples. However, it's also very low quality and blurry. For this reason, most game engines use some kind of hybrid approach, such as combining MIP mapping with hardware anisotropic filtering. So far, those techniques I described are considered obvious, common knowledge, and almost axiomatic. We don't really question them. I think that one of the reasons for this is that all modern graphic APIs have standardized filtering working exactly this way with some simple filters, such as low-quality bilinear filter or trilinear filter, and a slightly higher quality partial anisotropic filter. All modern GPUs have dedicated filtering hardware that, on most texture formats has zero additional cost for filtering. Even anisotropic filtering is significantly cheaper than doing this naively or manually in shaders or in software. Because of this low cost and common support, it's very easy and attractive to use that traditional framework without questioning it and, let's be honest, without thinking too much about it. This creates a feedback loop. We use it because it's easy, and then the next time we want to do texture filtering, we assume it's the correct or maybe even the only way. This is just the way we do texture filtering, right? This brings us to our initial motivation. The case when we could not use hardware filtering, and because of this started to question everything we knew about texture filtering in graphics. Last year, at SIGGRAPH 2023, we presented a paper, Random Access Neural Compression of Material Textures. This technique uses neural networks to achieve significant compression ratios that are substantially better than those of hardware-supported block-compressed formats such as BC1 to BC7. And one of the goals of our paper was that, unlike prior work on neural image compression, we didn't want to limit ourselves to transcoding or decompressing into virtual textures, but additionally allow for using compressed textures directly in the shaders to save both the disk storage and memory. It turned out that it's possible, and on a modern NVIDIA GPU, the decoding cost for multiple textures belonging to a single material can be approximately 0.6 milliseconds at a 4K screen and texture resolution. For details, please check our previous paper. However, there was one challenge. This representation by itself does not support texture filtering, such as bilinear or trilinear filtering. Most papers on neural compression ignore this issue and don't show any examples of magnification filtering. It was important for us to be practical and able to replace traditional BC material textures in all scenarios common in real-time rendering, so we had to tackle this issue. One way to filter our neural textures is to run this neural network 4 times for bilinear filtering or 8 times for trilinear filtering, increasing the cost substantially. So, instead, we proposed evaluating filtering stochastically by randomly jittering UVs with different jitters every frame, and then using nearest neighbor sampling on those jitters UVs, and finally relying on temporal reconstruction to remove noise. This worked very well. I will explain this method in detail later in this talk. First, however, I want to emphasize that we were not the first one to introduce this concept. It was used for 30, maybe 40 years, and numerous precedents exist in literature and practice. Please see our paper for a full review and discussion. Interestingly, those techniques were used by both offline rendering and even very early video games. Nowadays, advances in temporal reconstruction, such as temporal anti-aliasing, temporal super-resolution, and temporal super-sampling, make all the stochastic techniques even more attractive. Temporal integration filters such as DLSS use machine learning for gray denoising quality without visual artifacts. In this work, we generalize and formalize those prior approaches and propose 2 families of techniques beyond those simple filters. But we have a more important problem to solve first. Namely, visual results can look significantly different. The inset D of hardware bilinear filtering differs significantly compared to inset D with stochastic texture filtering. We expected a visual difference, but at some point we started brainstorming and having many discussions about it, which led us to question everything we knew about texture filtering. Which way is correct? How does one even define correctness? A second, bolder question started forming in our discussions. Maybe we are teaching and using traditional filtering incorrectly? However, to discuss correctness, we cannot rely just on our intuition. We need to formalize it, make some assumptions, and analyze when those assumptions are fulfilled. We also reviewed 40 years of computer graphics literature to see if this problem was discussed before. And it was. The first example mentioning this problem comes from Porter and Duff in Compositing Digital Images, where they discuss alpha blending. They observed that when textures with transparency masks are filtered, and those filtered values are multiplied directly using alpha blending equation, the result is incorrect. Incorrectness manifests itself here as those ugly halos around alpha blended objects. The reason for those artifacts is simple. A multiplication operation is nonlinear, and we cannot swap nonlinear operations with interpolation and expect the same results. Mathematically speaking, nonlinear functions and interpolation do not commute. So, how did they solve this problem? They simply multiply the color and the alpha value and store those multiplied values in the texture itself. And this application of nonlinearity before filtering removes any error. This is the first instance of what we will call filtering after shading, where a nonlinear shading function is applied before filtering to ensure mathematical correctness and also a better visual outcome. Reeves et al. Made a similar observation 3 years later in Rendering Anti-Alias Shadows with Depth Maps, where they introduced the concept of percentage closer shadow filtering. They demonstrate that one cannot filter or average different depth values and then compare them with a shaded point depth value. Those averaged and interpolated depths are nonsensical. They don't correspond to any object in the scene. Filtering depths and then applying comparison shading nonlinearity produces visual artifacts and generally completely wrong shadow shapes. So, what do they propose instead? A very similar solution. Apply a comparison nonlinearity first, which yields a binary mask, which then can be filtered or averaged, producing correct values and softer shadows. As a side note, in modern renderers, shadow map filtering is also often performed stochastically to allow for wide shadow penumbra without prohibitive shadow map sampling cost. Reeves et al. Conclude the paper with a very interesting paragraph where they hope to be able to generalize this observation and formalize those transformations of percentage closer filtering to other texture uses in rendering. They noticed that it should apply to more applications, not just shadow map filtering. For example, bump mapping, often now known as normal mapping, where specular reflections look significantly different when naively filtering values in bump maps or normal maps. The literature addresses this very specific problem of specular minification and specular appearance change in many publications. Numerous papers are available, and they are often called specular anti-aliasing or specular appearance preservation. Those solutions typically adjust other BRDF properties to compensate for the appearance change from flattening the normals, but they don't attempt to generalize it to other filtering-related errors. Error coming from texture filtering keeps coming back in contemporary rendering. One example is the so-called metalness PBR workflow, where a special texture channel called metalness is introduced to save the storage cost of separate diffuse reflectance and specular reflectance textures. The metalness channel interprets reflectance color as either diffuse reflectance for dielectrics or specular reflectance for metals. However, interpolating base color and metalness results in halos and visual artifacts that are very similar to non-premultiplied alpha blending. And it is caused by exactly the same nonlinearity of multiplication. Again, multiplication and other nonlinear operations do not commute and cannot be swapped with filtering. Reviewing the literature helped us understand why traditional texture filtering is explained this way and why, in modern rendering, it introduces errors. Texture filtering theory and practice were initially developed for interpolating just color. In the earliest work, not even gamma corrected. And filtering and affine functions commute perfectly. This approach didn't introduce any errors, and you can swap them arbitrarily. However, nonlinearity and nonlinear shading functions and filtering do not commute. Swapping the order results in error. To define correctness, we make one assumption. Textures are authored by artists with roughly a 1:1 pixel-to-texel ratio. This is not a very strong assumption and holds for the vast majority of assets. There are some specific examples and use cases where this assumption might be violated. I will demonstrate them later during discussion of our results. However, this is reasonable and not very strong for most textures. Under this assumption, minifying or magnifying textures before nonlinear shading introduces error and bias. Different techniques were proposed to address very specific and use case dependent types of errors. However, we want to answer a more general question, the question from 37 years ago. Can we do better in general? And if so, how to do it efficiently? To introduce our findings and the proposed method, let's start by reviewing one of the most common uses of textures in rendering, the rendering equation. Here is a familiar integral of all possible incoming lighting directions and incoming gradiences that are multiplied by an angle-dependent reflectance function and the solid angle term. This is just an example of what we call shading, but shading generalizes also to other nonlinearities. The reflectance function itself is typically not just a constant function. Most of the time it's spatially varying and depends on some input textures, such as normal maps, reflectance maps, or roughness maps. To compute the BRDF function, we evaluate integrals that correspond to texture filtering, where a texture filter function is multiplied by different texture samples. This is filtering before shading, and because of the nonlinear nature of all modern reflectance functions, it introduces error and bias. Here is an example. A traditional filtering approach using hardware introduces significant specular aliasing and a vastly different appearance as compared to a supersampled reference. Our proposed approach, filtering after shading, swaps the order of those integrals. First we shade, and then we filter the results. Before explaining our method, here is a teaser of our approximate real-time implementation of filtering after shading, preserving the original appearance significantly better than filtering before shading. But how do we realize this swapped order of integrals in practice? If done naively, we would need to evaluate lighting and shading many times for each texture sample. Furthermore, it's unclear how it would work for a case with multiple UV sets. To solve this integral, we propose the most common approach to integration in computer graphics, Monte Carlo. We take single samples from the filter, and we can construct an unbiased estimator. For details and derivation, I'll refer you to our paper. This estimator uses only single unfiltered samples. One could take multiple samples from this estimator, but we propose an extreme solution, an extreme take. Only one sample whenever you evaluate the BRDF. As expected, single sample Monte Carlo results in a lot of noise, especially when using white noise and looking just at a single frame. However, when we use robust temporal integration, such as DLSS, the appearance of noise is reduced dramatically. When we use spatiotemporal blue noise instead of white noise, even a single frame appears significantly less noisy. When combined, spatiotemporal blue noise makes the job of DLSS significantly easier, and in most practical examples, we can see no noise anymore. Let's have a look now at two separate families of methods we propose to evaluate those filters. The first of those families of methods works in the discrete domain. The continuous integral of the product of the filter and the texture values corresponds to a discrete sum because texture values are defined only at singular points of Dirac deltas. We have a sum of a set of discrete values, and we can pick one sample with probability proportional to the filter value. Since all weights of valid filters sum to 1, this is already a valid discrete PMF. Effectively, this is important sampling. We sample a text cell with probability p proportional to the filter value, and this is optimal approach if we don't know the signal and we cannot sample the actual filtering product. We can sample the array of weights by evaluating all of the filter weights and filter function, constructing a discrete CDF and sampling from it, or we can sample online through weighted reservoir sampling. Again, details are presented in the paper. Most texture filtering multidimensional filters, linear, B-spline, Mitchell-Netravali, Gaussian, are separable. This is great because we can sample from each dimension separately, which dramatically reduces the filter's cost to just n taps times d dimensions and not n to the power of d. This family of techniques works very well, but can be costly with very large filters, even if they are separable. It does not support infinite filters, such as Gaussian or sinc filter. And obviously, one can truncate or window those filters, but it can introduce errors. Luckily, there is a second different way in practice for many applications, such as our prior work on neural texture compression, UV jittering and nearest neighbor sampling. Let's analyze and understand it in detail. What happens when you take a nearest neighbor sample? This is also a texture filter, a box filter. It is equivalent to convolving those infinitely small Dirac deltas with a box kernel with the width equal to the text cell spacing. Okay, so now what happens when you first jitter the UVs with the magnitude of one text cell size before using the nearest neighbor sampling? This is a convolution of two box kernels, one from jittering and one from nearest neighbor sampling. The convolution of two box kernels is a linear kernel or tent kernel and yields linear interpolation. Understanding this convolution of two kernels, we can generalize this technique to other types of filters. For example, we can create higher orders of the B-spline family kernels using the Cox-de-Boer recursive formula. If we use linear UV jittering followed by nearest neighbor sampling and its box kernel, we get a quadratic B-spline. If we jitter with a quadratic B-spline PDF and follow it by the nearest neighbor, we get a cubic B-spline. In 2 dimensions, this is a bicubic kernel, smooth but very pleasantly looking. It is a close approximation to a Gaussian kernel and is often used in offline rendering for magnification. This sequence of repeated convolutions of box kernel with itself, it yields higher and higher order B-splines. A box filter from nearest neighbor sampling is highly desirable for B-spline family because we can sample or jitter order n-1 B-spline and then get an n-degree B-spline filter at a smaller performance cost. However, we can also sample other filters, including infinite spatial support filters. We would need to jitter UVs according to their PDF deconvolved with the box kernel to do this. Unlike B-spline filters, most filters don't have a closed form deconvolution with a box kernel. However, this additional box kernel can still be advantageous, for example, for the Gaussian filter, and we explain this in our paper. This method allows us to sample infinite filters, such as the Gaussian filter, using the very efficient Box-Muller transform. The jittering range is theoretically infinite, but in practice concentrated around the evaluated points. To sum up, comparing those two families of methods, the main difference between them is the domain, discrete and operating on individual filter weights for different samples versus a continuous PDF of the texture filter and doing UV jittering in this continuous domain, followed by the nearest neighbor sampling. Both methods have their use cases and pros and cons. For many cases, the discrete domain is the only option. For example, for arbitrary discrete kernels, or the technique called positivization we described in our paper and used for sampling filters with negative weights. Otherwise, when possible, we recommend continuous filter importance sampling due to its significantly simpler and more efficient implementation. We provide source code and comparison in the supplementary material. And we could use either of those approaches for minification by finding pixel extents in the texture space and using either trapezoid jitter or, for example, elliptically weighted averages. However, computing this mapping is rather costly and unnecessary. There is a much simpler and already used method present in practice and in production. Most modern renderers jitter the camera projection matrix for the anti-aliasing reconstruction filter. And again, both offline film rendering and real-time rendering. This jittering is done for anti-aliasing and super resolution. This uniform jitter of 1 pixel in screen space corresponds to a trapezoid in the texture space, which is exactly what we need. Many renderers that use camera jitter and the negative MIP bias already apply a form of filtering after shading. No additional steps are necessary for minification if the renderer already uses some form of anti-aliasing reconstruction filter. Only sampled MIP levels need to be adjusted. For pure filtering after shading, disabled completely. We only add a UV space jitter to handle magnification and minification in the shader codes. There are no specialized cases and it's very simple to implement. Those two jitters are different in magnitude depending on the minification or magnification. When we minify, then the UV jitter is negligible and pixel space jitter covers many text cells and dominates. Conversely, when we magnify, the pixel jitter is negligible and close to zero as compared to the UV jitter, which spans many pixels. We knew that our approach results in a different appearance and for minification, appearance preservation. But we also need to understand the appearance changes during magnification, where no supersampled reference exists. This is the example that motivated our investigations, a figure from the neural texture compression paper, where we compared traditional filtering with stochastic filtering after shading. We observe that specular appearance is significantly different. Traditional filtering has a highly specular, glossy, foil-like appearance, which is not present in filtering after shading. The reason for this is simple. Filtering before shading corresponds to interpolation of normals and effectively interpolation of the surface curvature. In this case, two separate facets correspond to two different texels pointing in the opposite directions. With filtering before shading, the interpolated surface normal points directly towards the viewer and the light direction, producing a high specular localized peak. By comparison, filtering after shading evaluates lighting only at the directions present in the artist authored normal map, and thus this sharp peak is never produced. We are filtering lighting values and not reproducing the surface curvature. In this specific example, I think filtering after shading looks better, but this is very subjective, and it obviously depends on the artist's intent. It's neither good nor bad by itself, and it depends on this intent, but it changes the appearance, and thus artists must be aware of this behavior. But this is where our original assumption of textures are authored by artists with 1:1 pixel-to-texel ratio sometimes can be violated. For example, artists might have wanted the surface to be very smooth. They might have relied on the reduced texture resolution to save memory, assuming that it would produce a smooth surface. In this case, this assumption would be violated. One extreme example of relying on interpolation is signed distance field fonts, where one can reduce the resolution of binary alpha masks for fonts and other cutouts by storing it as a low-resolution distance field, upsampling, and only then applying nonlinearity. This kind of optimization and approach would not work with filtering after shading. There is an even worse example and limitation of our technique. It can cause aliasing. Here is one example of specular material where filtering before and after shading looks significantly different. But the main problem here is not different appearance. In my opinion, it's those jagged lines and aliasing. For a long time, we have not seen this in practice. This example was provided to us by our colleagues from the DevTech team. I think this emphasizes that research is never finished until you try it in production and collaborate with others. This problem was not observed on most assets by our colleagues or us. However, in some assets, it shows up, and at first, I thought that there might be some bug in the stochastic evaluation of filters. However, this problem is also visible when evaluating this integral non-stochastically. So, what's going on? The problem is aliasing introduced by a nonlinear function. For a formal analysis and detailed explanation, please see the paper. However, I'll try to sum it up informally and intuitively. Any nonlinearity always introduces higher signal frequencies, called harmonics, that are multiplies of the original signal frequencies. For example, when we apply squaring nonlinearity to a sine function, we get a sine wave of twice higher frequency plus a constant. The same happens for further powers and all frequencies present in the original signal. They generate higher harmonics that are sums and multiplies of the source frequencies. In signal and audio processing, this is called intermodulation. Every single non-trivial nonlinearity introduces higher frequencies and higher harmonics. Audio processing has developed theory and practice for analyzing those, as higher harmonics are essential for generating or avoiding audible distortions. When these additional higher frequencies are created on discrete signals and exceed their Nyquist limit, they alias immediately. The amount of aliasing depends on the use of nonlinearity, original spectral content, and the relative phases of different frequency components. Here is an example of this exact sine wave sampled slightly below the Nyquist frequency. We get an almost contant and completely different wave when we square those discrete samples. At the evaluated discrete points, values match, but we miss the variation in between. Given this discrete grid resolution, the correct continuous signal, twice higher frequency, is simply not representable. This might seem an extreme and contrived example because we have values between -1 and 1 and square them. So, I will demonstrate a second, more practical or relatable example where the nonlinear function resembles specular shading. We have a highly nonlinear function with a peak at 0.5 that goes rapidly towards 0 outside. We also have a signal here sampled around the Nyquist frequency, and it can be reconstructed perfectly using high-quality interpolation such as windowed sinc filtering. Applying this nonlinearity at evaluated discrete points and then interpolating produces a completely wrong result, presented here as the green shape. This is exactly aliasing in action. The original signal was critically sampled, but those new higher frequencies are not. The interpolated orange curve can represent them correctly after applying the nonlinearity. What does this nonlinearity-introduced aliasing mean in practice for magnification? During magnification, screen Nyquist is higher than the texture Nyquist. If we magnify a texture first, we have significantly more headroom before the Nyquist frequency and before aliasing happens. If we apply nonlinearity first, we alias immediately and then upsample those aliasing artifacts. However, the opposite happens during the minification, where screen Nyquist frequency is lower than texture Nyquist. Thus, we have more headroom in the UV space with filtering after shading. We apply the nonlinearity, and then filtering can remove most of the nonlinearity introduced aliasing. This explains why filtering after shading removes aliasing for minification, while it can introduce some aliasing for magnification. Let's have a look at some results now. I have shown teasers from this figure before, and it demonstrates our real-time implementation of stochastic minification. We compare the reference taken at a significantly higher resolution to traditional filtering before shading with different configurations using single ray tracing and the DLSS. We explain those configurations in the paper. No matter which configuration is used, filtering before shading introduces aliasing and changes the appearance dramatically and unacceptably. A single frame is very noisy with filtering after shading, but DLSS removes the noise almost completely, preserving the appearance. In practice, we recommend a hybrid approach for real-time rendering, still using MIP maps but selecting a MIP map of much higher resolution than the one that would be used by the hardware. The reason for this is to reduce cache trashing, improve memory bandwidth utilization, and make temporal integration easier in motion. This hybrid approach does not perfectly match the reference, but it is very close, and we believe this is a reasonable practical compromise. Appearance preservation also applies to 3D textures and volumes and offline rendering. Here is an example of a 3D texture that stores temperatures for an emissive volume, which are then converted to an emission spectrum using nonlinear Planck's law. With traditional filtering before shading, the minified result significantly and acceptably differs from magnification and translation. By comparison, the stochastic evaluation of the minification filter after shading has the same and correct visual appearance as stochastic trilinear after shading. Another interesting and possibly surprising aspect of stochastic texture filtering in offline rendering is that it doesn't usually introduce additional noise. Here is an example of volumetric cloud rendering through Monte Carlo integration. This integral needs to take many more samples than a stochastic texture filter. Stochastic filtering noise is negligible compared to volumetric Monte Carlo integration noise. So, in this example, with stochastic texture filtering, we can use better quality filters, such as smooth and nice tricubic, unlike ugly and jagged trilinear, while being significantly faster than non-stochastic trilinear filter. It's a pure win on all possible axes. Let's examine now how DLSS handles noisy texture filters in motion. We show hardware filtering using anisotropic filtering on the left, and on the right are stochastic bicubic filtering. We cannot really see any noise, ghosting, or flickering, and it behaves very well under motion. When we get closer to the surface, I argue that it looks significantly more pleasant and better than traditional filtering, just because we are using a less aliasing filter, namely stochastic bicubic filter, which is better filter than bilinear. We also wanted to stress test our algorithm with the most challenging high contrast and high frequency content, checkerboard and zero MIP map use. Single frames are obviously very noisy. Applying DLSS and accumulating it over a few frames removes most of the noise, but some noise and aliasing remain. However, it's still significantly closer to reference than hardware filtering. The case is similar for magnification, where single frames are very noisy and there is also residual noise after DLSS. We'll now discuss our results and findings and follow with some practical recommendations, starting with the issue of remaining noise. From the practical angle, we believe that this problem is rather small and not very bothering, and it will get smaller and smaller every year thanks to temporal and reconstruction filter improvements. Every year, we see amazing improvements in ML-based algorithms, and they are trained on data, and we can include those noisy frames in training datasets. Furthermore, we also see annual advances in better spatiotemporal blue noise patterns and other low discrepancy patterns that can be used to minimize noise before we even apply the temporal filter. This also fits the overall trend in computer graphics, where Monte Carlo methods are initially too noisy or too slow when taking multiple samples to use in practice, despite numerous advantages, such as being unbiased, simple, and more general. For a while, semi-analytical models are used as a workaround due to their lower cost and lack of noise, despite the introduction of bias, complex implementation, and limitations. Then, over time, Monte Carlo and stochastic methods slowly become practical and begin to take over. This was the case with geometric anti-aliasing. Temporal filters have almost completely displaced MSAA, and similar variants were possible. Shadow map prefiltering techniques are becoming obsolete in the age of ray trace shadows. Finally, offline rendering has moved almost exclusively to path tracing, and we even already have some path traced games. Let's look at some applications of stochastic texture filtering beyond the correctness of filtering after shading. I mentioned that our motivation for investigating stochastic texture filtering was neural texture compression. Here is an example from the last year's paper. We can store around 16 times more texels than BC textures of comparable storage size with new compression formats. The evaluation cost should be acceptable even for the most performance-challenging video games, thanks to stochastic texture filtering. And this application is obviously not limited to neural texture compression. In the paper, we evaluate using DCT compression and show that stochastic texture filtering saves significant performance. It also applies to all kinds of other representations and compression formats. For example, neural VDB uses octrees together with small neural networks for super efficient compression of volumetric textures. I think the development of new compression formats, not limited by hardware filtering support, is very exciting and very relevant today, when game downloads, disk storage, and memory usage are becoming prohibitively expensive and a limiting factor in rendering detail and quality. An additional application of stochastic evaluation is any kind of interpolation or blending of material properties. Here, again, we cannot just blend different material properties and expect the correct results. One example that we demonstrate in the paper is stochastic triplanar mapping and 3 times reduced sampling cost. I believe some game developers already practice it, but we show that it's not just a performance-saving hack, but a more correct and unbiased approach. Stochastic texture filtering allows for the use of much better texture filters. You are not limited to an ugly bilinear or trilinear filter, but can use any that is better suited for your specific application. It can be a smooth B-spline bicubic, radially symmetric and even smoother Gaussian filter, a sharp Mitchell filter, or maybe an over-sharpened Lanczos filter. Those are just examples. It's up to you. But stochastic texture filtering can be used for almost any kind of filter, including negative lobe filters. Our recommendations are as follows. For minification, we believe that filtering after shading is always better. Offline rendering can completely eliminate bitmaps, as the rendering Monte Carlo noise dominates stochastic texture filtering noise. We still recommend a hybrid approach for real-time rendering that balances performance and temporal stability against the remaining bias. For magnification, there are pros and cons that need to be considered. Filtering after shading is unbiased and it removes error, assuming that textures were authored with 1:1 pixel-to-texel ratio. It simplifies logic and removes specific workarounds. For example, one does not need to take care of the premultiplied alpha because it's done automatically by our framework. It allows for metalness workflow, and it can also remove texture padding for virtual textures. It allows for better, higher quality filters, new texture representations, and compression formats. One does not need to worry about the presence or not of hardware filtering and additional cost if it's not supported. However, filtering after shading can introduce some aliasing during magnification, and sometimes it can look very unpleasant. I'll note here, however, that if, for instance, by using some novel texture compression format, you can get 16 times better compression and 16 times more real texels, you don't need to rely on interpolation and magnification anymore. And it's a significant quality win. Similarly, higher order filters that alias less than bilinear filter can still result in less aliasing even when using filtering after shading. We recommend a pragmatic approach. You don't have to go all in. For magnification, there are trade-offs in cases where one is preferred over the other, and we definitely would not recommend stochastically sampling something that relies on interpolation, such as signed distance field fonts. You can decide whether to use filtering after shading, stochastic texture filtering, or a different filter per asset or texture type. Only a few lines of shader code change, so it's extremely simple to just test and compare. To conclude, filtering after shading might seem radical because we propose to rethink everything we know about texture filtering and how we've been using and teaching it. However, we simply formalize decades of the different film industry and game dev practices and observations that filtering after shading is unbiased and better for appearance preservation. We need to change how we teach and think about texture filtering, and even if we choose the traditional approach for a specific use case or pragmatic reason, we must be aware of the trade-offs. Similarly, stochastic texture filtering has been present in the literature in various one-off flavors for almost 40 years. We explain those approaches and generalize them, proposing two families of techniques with different trade-offs and different applications. We expand those prior approaches to more filters, including negative lobe filters. We provide efficient implementation with minimal source code and a very non-invasive way of integrating. In summary, filtering after shading by stochastic texture filtering is a valuable tool. It is unbiased and correct, better at preserving appearance at multiple scales. It removes workarounds and simplifies code. It enables efficient filtering of novel compression and storage formats. It allows for efficient, better filters and applies beyond textures for stochastically sampling complex shader graphs. Finally, it is already practical today with a high-quality spatiotemporal integrator such as DLSS. Give it a try. We want to thank our colleagues across the company for their contribution and project support. You can learn more about our paper on the project website, and thank you for listening.